Okay, so for this one here, we're going to talk about two things. We're going to talk about the difference between through-hole components and surface mount components, and through-hole pads and surface mount pads for the pad stacks. So um, first off, let's just look at a circuit board here. And I know this image is a little fuzzy. I'm going to have another one that I'm going to pull up here. But this has a good combination of things that are both through-hole and surface mount here. So most though of what is on here is what would be considered surface mount here. And there is actually a blank spot here where a component hasn't been placed. And these would be considered, these little four rectangles that I'm kind of going around are considered surface mount pad stacks. And the reason they're called surface mount pad stacks is that there are literally it's being mounted on the top surface of the board. It's being mounted on the surface. And that's where the solder would also go. So you can see these components right here are ceramic capacitors. And you can see this little silver end on both ends is a metal contact for that capacitor. And you can see it's touching these two, and it's hard to see on this image, and if I blow it up, it's probably even worse. Yeah, there's actually it doesn't look like it, but there's a gap in between those pad stacks. I'll see if I can find an image that will show you that better. And so that gap there means that basically one side of this is soldered to here, and the other side is soldered to this side. And you can see this little line here is the copper trace that's been covered up by the solder mask that's moving to other parts of the circuitry. Another type of component that's a surface mount is this. This is actually an SOIC package. And one way you can tell that these are is that if you look at the way that these legs are, or the leads on these, is that if you were to kind of lay these on the board or hold them up to the board, the actual legs are bent 90 degrees, and so they're kind of, parallel to the board surface. And so it would obviously just kind of lay on top of it, and then you can see there's all these little things that I'm pointing at. Those are all rectangular surface mount pads. And then the component actually gets soldered to all of these components here. And if you look at some of the videos that you guys are looking for during the discussion board this week, you'll actually be able to see some of these components being placed. Now, the through-hole ones would be things like this here. You can see there's a metal pin that's coming out of the bottom of the board, and this is probably to mount into something else here, to connect into something else. But the pin has come through the hole that was drilled into the board, and then they soldered it. So the reason they're called a through hole is the way you would envision this is that this metal spike here on the bottom of the board, that's the connector. So the connector is mounted on the bottom side, but you're soldering it on the opposite side of where you're mounting it. So a through hole component always gets soldered on the opposite side of where you mount it, where a surface mount always gets soldered on the same side as where you mount it. And you can see there's some other through hole pins up here, and you can again see the traces coming off of them. Alright, so let's look at another one here. This is just showing the difference between, again, these are a bunch of resistors. And so this is through-hole resistors, or sometimes they're referred to axial, because these legs you can bend down easily, and then you would slip them through the holes in the board to solder them. Here, these are resistors, all of them still, but these would actually be mounted and soldered on the surface. And I had a Google here, so this particular image here, let me open this one up. Whoa, I didn't want to do that. This particular image is also kind of a nice one here. So it's showing here this is a through-hole resistor, but what's important to see here again is the fact that there's a circle that was drilled here, and then that lead went through the board and actually got soldered from the bottom side. Even though it looks like it might have gotten soldered from the top, it didn't. It's just the reason there's solder there is kind of a capillary action when the solder came on the bottom side. And then this actually here is another example of a through-hole component, although it's not obvious. But you can see the other side again is going through. Now, without going into detail here, this got a couple. This is actually ground here, and then this would go to additional parts of the circuit. Now, surface mount, again, these are, well, these might not be resistors, but they look like they're resistors. And you can see there's solder right here, and solder right here. So they got soldered on the top side of the board, and there's no hole that was drilled. Now, as another interesting thing here is this right here, as well as this one right here. Remember we talked about vias. Those are actually two vias that are just on this picture here. So what that means is, you see there's this wire, but then that means that this trace also jumps to another layer, probably just the bottom side of the board. But then it also continues on to other connections as well. All right, so how can you tell by looking at a component whether it is a through-hole or a surface mount? Well, the reality is almost all your components are going to be surface mount as far as if you're looking on a website for components. But you can specifically try and find through-hole components. There are not very many packages of them, but let me show you some ways you can tell that these are through-holes. For instance, I'm going to do an LM317 datasheet. And I'm also going to talk about datasheets at the same time. Oh, I don't want the online datasheet. Oh, come on. Technical documentation. There we go. Okay, so first off, a data sheet. There's 31 pages. There is an overwhelming amount of information in a data sheet, and I know some of you had commented about that. Most of this information at this point in time is stuff that we can ignore. Now, always at the top of data sheets are going to be what they consider some of the key features. Now, one of the things that we're not going to, again, concern ourselves with is we are not actually designing circuits in this course. We are just learning about some basics of doing some very fundamental simulations like we did, and then we're going to learn about how to do a layout of a circuit, because we can do a layout without actually knowing how the circuit operates. So now you can do better layouts when you know how the circuit operates, but we can still do them without knowing it. The next section usually is always going to be, well, what are the applications? And there's a lot of them here. You don't really need to read that. Then they're going to have a description of the device. Most of this that I'm going over here right now is not stuff that we will ever be interested in this course. Now, let me talk about the things we will be interested in this course. And they're always at the end of a data sheet. What we are going to be interested in is if they have any layout guidelines. And we're also going to be interested in mechanical and packaging and ordering information. Okay, so let's look at the packaging, because that's going to tell me whether it's a surface mount or a through-hole, or in some cases you're going to have multiple options for the type of package. And so as a user, when I would order the part, I would have to determine the type of package I wanted. So let's go to page 19. That's about ordering it. So I can tell now that this particular one, this is called a flange mount package, plastic. This is a surface mount component. How can I tell? Well, look how, first off, notice that these pins themselves are not that long. That's an indication that it's going to be a surface mount component. Also notice that the pins do not extend below the package. If it was a through-hole component, this portion here would be bent 90 degrees so that I had a vertical line going through here for the lead. This picture doesn't really help me because it looks like, oh, well, it looks like those things you could like kind of insert into a board and it could be a through-hole component. And then there's this exposed thermal tab. Now this exposed thermal tab is then used for heat dissipation because this device actually generates a lot of heat. And then it's got some more information, and we can see that this datasheet gives a example layout, and it's giving the copper area, stencil design, solder mask openings, things like that. I'm just seeing if there's another one. Here, plastic small outline. Again, this is another surface mount component because look at how the pins are corresponding to the package. See how the pins are corresponding to the package? That's another surface mount component. Okay, now here's a TO220. Now this is a through-hole component. How can I tell that? Well, first off, just look how long these pins are. And also, this is the bottom of the device here. And let me just see if I have the ability here. I'm just going to download this for a second. And go back to that page here. It's highlighting text. We'll see if this works with the diagram. But if this was a surface mount component, yeah, it's not going to work very well. This pin here would have to be flush, like this would be bent down and then bent out, and it would probably be cut off like right here. And so that's how we can tell that this is a surface mount component. Plus another, no, I'm sorry, not a surface mount, a through-hole component. Because a surface mount, again, would have it so that all of these pins would be flush so that it could lay flat on the board. And you see there's no way that you could lay this, because this is like the back of the board, or the back of the part. There's no way you could lay this on the board and have these be flush with the board. So it's a through-hole package. Also, notice that there's a hole drilled through on that metal tab, and that's to be able to attach a heatsink to it. Let's see if there are any other package types. Well, now it gives an example board layout. Now this actually answers another question that came up. Why do we have square pins sometimes and circle pad stacks sometimes? We'll show it in another package here, and it's that, well, they're looking how there's the round hole to drill the hole. Okay, good. Okay, we got the round hole to drill the hole, but then there's this square copper pad. Why do we have a square copper pad there? Well, notice here, pin 1, 2, and 3. And so pin 1, 2, and 3, if I go up here all the way back to the very beginning, I went too far to the beginning. Here, pin 1, 2, and 3. Pin 1 is called the adjust pin, pin 2 is the output, pin 3 is the input. So it's very important to know which pin is the adjust, output, and input, because you have to know how to wire the circuit up properly. This is just an example of how it would work. Here's the input voltage, here's the output voltage, here's a couple resistors, and this adjust. Now, again, I am going to be giving you all the designs for this course, but why you would want that square then is that when these devices are actually being placed for a through-hole component, it picks it up and it might have to rotate the component. And believe it or not, these machines that do this automatically have cameras, and the camera can take a picture of this and say, oh, this is the square pad, so I know that's where pin 1 goes. So I know that I need to put the component in this direction. And it also can help us when we are starting to assemble boards by hand, because when we say, oh, that's the square pad, that's where pin 1 goes. So we figure out what pin 1 is on our component, and then we know that pin 1 goes there. So it tells us the orientation of the component. Because imagine this component here, if we're looking at this particular one, there is 2 ways I could put it in. I could put it in, and then I could also rotate it 180 degrees and put it back in. One way won't work, and the other way will work just fine. That's why we use this square copper pad. Now, the circle, again, the hole is still a circle that we're drilling because, well, we're drilling a circle for these 3 pins. We're just, again, using this copper pad to indicate this is where pin 1 goes. So let's look at another data sheet here. Oh, before we move on to another data sheet, let's go to look at the layout. So there's this layout guideline here. So now this is for one particular type of component. We looked at the 3 different packages, and this was where it had the tab mounting package here, and it's got the output here and this C out. It's got ground here, power coming into the input, and some other capacitors going on there, and the resistors, and there's this other capacitor which we don't have to talk about. But what this is saying is that when you see a schematic, it's going to have these components here. Now, it's not going to necessarily label them R1 and R2, but there's going to be 2 resistors that are going to be connected to this LM317, for instance. And it's saying, well, the way you should wire it is that you should have R1 kind of located in this area, R2 located here. You should put ground over here. You could, and then there should be ground over here. Now, these are the same ground, and they'd be connected in different ways for the board. And then this is where your output should be, this is where your input should be, and this is how you put your capacitors, down, etc. So it's giving us the information on how to do the layout for this component. Now, it's a good guideline, and in some cases it's very critical to follow it. In other cases it's not as critical. But anytime they have layout guidelines, it's always important to do it. And it even talks about some of the guideline kinds of things. Says, recommends using wide trace lengths to eliminate the I times R drop and heat dissipation. So what the wide trace lengths, that's talking about, notice these gray areas are the traces, and it's saying using wide lines for that. All right, so let's look at another data sheet. So let's look at an LM386. Now this is an audio amplifier, and actually you can use this as an audio and amplifier. It's very like legacy component in the sense that it's not really used anymore, but it's still used as hobbyist and everything. So went too fast here again. I was just going through. So again, looking at the table of contents, features, applications, description, revision history, pins and functions, specifications. All of this is stuff that you'll learn about as you progress through. So if you're feeling overwhelmed by the data sheets, don't worry. I felt horribly overwhelmed when I first started reading data sheets. And the more you read them, the more you get used to pulling out the information you need. Now for, again, this course, we're just going to look at layout and mechanical packaging. So let's do the mechanical packaging. So, this is, again, for ordering information. This, by the way, here, this is showing how the component will be delivered. And you notice how there's this little tape here. These are tape reels. It's literally a reel of components. And then, as these machines go through it, it has these little things where it's kind of like the old style printers where they had these dot matrix printers where they would actually use things to move the paper through. They use that to move the tape reel, the sprocket holes, and then basically it picks up a component. Each one of these has a single component in it, and then the machine will pick it up and then place it, and then it will move to the next board. And so for this one, okay, this is an SOIC package. Now, what's kind of nice is this picture here right away to me shows that it's a surface mount. Look at how the pins are. They're flush with the bottom of this component or parallel with the bottom of this component. They run in line with it. And you can see here in the spec as well that they are. Now you might say, well, wait a minute, they're not quite parallel. There's a little bit of a gap here. Yeah, there is a tiny bit, but again, look at how the pins are bent. This is absolutely a surface component, surface mount. And then again, it gives you an example layout. Now here, this is plastic dual inline package. So this here is a through-hole component again, and that's easy to see. Is look where the bottom of the package is, and look how long this lead extends beyond the bottom of the package. So that's clearly that this lead is going through the board and being soldered from the bottom side. And then this is actually another package, plastic small outline package, which is different than SOIC. It's got different dimensions for these. They're actually a really big pain in the butt to solder by hand. And so it's got information about these. You can notice that these are actually much closer together, and that those are the three package types. Now, some components only have a single package type, but others have multiple. And again, why do you have multiple package types? Well, it depends on the application. The reality is this SOIC, I don't know this for certain, but the SOIC package is probably the cheapest because it's the most common one. This DIP one is probably a little bit more expensive because it's kind of, most people for these types of chips, they're not going to be doing through hole for this. They're going to be doing surface mount. So, but there is still some people that do through hole. And then this plastic small outline, it's very small, and so this would be for like, well, if you're needing something like this, for instance, if this chip was being used in a cell phone, well, you need to make sure you can get the smallest chips possible because you have space constraints. You don't have a lot of space to put your components down in a cell phone compared to like, well, just think of a computer motherboard. Compare the amount of space to put components down on a motherboard compared to a cell phone. And the reason I say it is they're both computers. Or even think about a tablet or a laptop versus a desktop. So now one other thing here on the data sheet, referencing that pin 1 having that square thing. Well, notice here that there's this little circle here. The chips are also going to always have some kind of indication where pin 1 is. And believe it or not, again, when these things get picked up, the camera will take a picture of how it's been picked up and will actually notice where this pin 1 is, and be able to then rotate the component very precisely so that when it puts it down, it puts it in the exact correct location. Now, we don't do anything different for representing pin 1 as far as on the solder pads, because for surface mount, because they're all rectangular to begin with, and you wouldn't want to make this round or something like that to be a distinguishing feature. Now, sometimes they do other things to make a distinguishing feature, like they might put a little dot like on the stencil layer to indicate where pin 1 is for it. So that as it's placing the component, again, there's some reference for it to know where it's placing the components. So hopefully this has made looking at the data sheets a little bit easier. Again, it's easy to get overwhelmed with information in here. There's a lot of information. But in any of these data sheets, we're looking for two key places: the mechanical packaging and possibly the layout. And again, I could look at the layout examples. This is using, actually this might be the DIP package guide, and this is the SOIC guide, or this might be, doesn't really matter, but it's got some layout examples on how, again, you would lay out, and actually even has here top layer traces, connections to ground plane, connection to power plane. So this is surface mounting, and basically what it's trying to do is that, again, in more complex designs, these are going to be what are called multi-layer boards, where you'll have an entire plane of just copper that's power. And so it's like, well, you just are going to go straight down to that plane, and you'll have an entire plane that's ground, for instance, and you're just going to go straight down to that plane to make those ground connections. So, but that's kind of a little over what we really need to discuss here. Hopefully you don't feel as nervous about these data sheets, because as you said, there's an overload of information here on these, but we're only focusing on a few areas in this course.